let's get started. So I'm going to talk about object lifetimes. I originally submitted the talk as a complete guide to object lifetimes, but I'm very glad that I changed the title because this is by far not a complete guide to C++ object lifetimes. So I'm talking about object and their lifetime. So the obvious question is, what are objects and what are lifetimes? Now, objects are sort of fundamental to C++. This is a quote from the C++ standard. We're going to get those a lot. So intro.object/paragraph 1 says the constructs in a C++ program create, destroy, refer to, access, and manipulate objects. So essentially, all the C++ program does is you manipulate objects, right? Without objects, we don't have any C++ programs. And I don't mean like objects in the object-oriented sense of the word. It's just like a term of art from the C++ standards. And everything we do is manipulate those objects. And to understand objects, we need to understand three things. The first is storage. Then we have value, and then we have type. So let's begin with storage. So essentially, in a C++ program, we have a bunch of bytes. And those bytes together form the storage of the program. And every byte has a unique address. So here we've got a bunch of bytes. Just that make up our program memory. And like I've highlighted one. And currently contains the bit value OX41. Now the question about value is, what does this mean? This is the bit the value gets in. It could be the 8-bit integer 65. It could be the character uppercase A. It could be the start of the string that begins with an uppercase A, and then we've got the rest of the characters in the following bytes. It could be just some arbitrary byte in the middle of a 32-bit integer, and we have to look up the surrounding context to figure out what it is, or so much more. And this is the value. So a good definition from value comes from elements of programming. So we've got the datum, which is a finite sequence of zeros and 1. And then we interpret those datum, those raw bits, and that then defines the value. And now who decides this interpretation? Well, this is the type. Right? A type describes the interpretation of a datum. So for example, the type unsigned char says we need to take 1 byte of memory, so datum is 8 bits wide. And this we then interpret this as an 8-bit unsigned integer, and this forms our value. Similarly, when we have an int, we have to take 4 bytes and interpret them at a 32-bit 2's complement integer. Or we can have a split string where we take 24 bytes, and then we take the first is pointed to a null-terminated sequence of char, and then we've got a size, and then we've got a capacity. So a type just describes how big a datum is and how to interpret it. So with that, we can understand objects. So an object is something that has a particular type and occupies a particular region of storage at a particular address, and there the value is stored. So here we have a bunch of objects. So for example, x is our object of type int. It currently stores the value 42. And then we've got an object of type float. It stores the value of 3.14. And then we can change the value of the object of x. And this is all what the C++ program does. We create objects, we put some values in there, and then we manipulate those values. It's important to point out that two things aren't objects. First of all, functions. Even though a function has an address, they're not objects. Right? The address is just, so only the actual object is a function pointer. And when we use a function, we just get a value that is the address of the function to create a function pointer. But the function by itself, even though it physically occupies storage somewhere in your program, is not an object by the C++ standard. Similarly, references aren't objects. They're simply aliases to objects. So we're only having one object. We call it x, and we give it the value 11. But then we also got an alias for x called ref, and this just refers to the object. So essentially, all properties an object have, like transparently get assigned to the reference, because the reference is just an alias to some other object, but not an object in by itself. Now, what is a lifetime? Well, an object has a bunch of properties, and the lifetime is just one of them. It's a pretty important one, because all other properties that you give to an object only valid while an object is in its active lifetime. And in particular, the standard makes it pretty clear that before the lifetime starts and after the lifetime ends, there are very significant restrictions on how you use the object. So you have to be really careful by using objects before or after the lifetime. So this is sort of a high-level overview of the object lifetime that we will explore the rest of the talk. So the first step is always allocate storage. Right? We need to put the object somewhere. Then we initialize an object, and this usually starts the lifetime. And I put initialized in quotes because that's not really necessary, but we see later on. Then we use the object, right? We can freely read its value, we can change its value, we can take its address, we can do whatever we want. Eventually, we're gonna destroy the object, which will end the lifetime, and then we deallocate the storage. And the details vary depending on what kind of object it is, but this is the general gist. Now, the terminology in the standard is a bit confusing. So the standard talks about the creation of object. This just means that essentially that we declare an object. We now have a thing which we can assign to properties, but it does not necessarily start the lifetime. We can imagine that the declaration of a thread local variable, as we'll later see, this will create an object, but no object is actually like physically exists until we actually launch a thread, right? It's just, we have an object, we created it so we can talk about it, but we didn't do anything at one time. On the flip side, the standard talks about destroyed, and this is actually a runtime property that ends the lifetime. So destroyed is a runtime operation that ends the lifetime, whereas creation is just an abstract term in order to introduce an object so we can talk about it. It's a bit subtle, but I try to be careful about it, but like usually we just, when we say an object is created and then this starts the lifetime, and technically this is not correct, like those are slightly different concepts. I try to avoid this thing, but if I don't, it's not, I just want to point it out for completeness. It's also important to point out that lifetime is something the standard invented. It invented it to describe the semantics on the abstract machine. Right? It has absolutely nothing to do with the physical CPU your code executes on. Right? Your CPU doesn't care about lifetime, just the C++ standard does. So all I'm talking about is talking about like what the standard says about it, and it has nothing to do with the actual hardware your code is running. And for that, let's get started. So there are various ways to create objects, and the most basic one is a variable declaration. So intro.object paragraph 1, an object is created by definition. Right? So we've got a definition. This will create the object and also allocate the storage and start the lifetime. And then we can just feed, use, and modify it. And when we reach the closing brace, we will destroy the object and the lifetime and deallocate the storage. Now, in order to understand exactly how long an object is alive and we have a variable definition, we need to first look at the storage duration. So the storage duration essentially defines the minimum potential lifetime of the storage that contains the object, and it is determined by how we create the object. And there are three kinds that we need to care about here: static storage duration, thread storage duration, and automatic storage duration. Let's begin with the easiest one. You're probably familiar with automatic storage duration. So essentially when we've got just a regular variable in a nil function as a parameter without any special keywords, the storage is created when the lasts until the block ends. So we've created two variables of automatic storage duration. So the storage allocation begins there. Then we create another one. We enter block, so this ends the storage of C, and then we end the storage of A or B, right? You're all familiar with that. Static storage duration is even simpler. Essentially, if you use like static or extern, those storage lasts for the entire program. So essentially here we've got a global and a static global and a function local static and a local variable declaration of a global inside the function. But all of those have static storage duration, which means that even before main starts, they have storage, and they will continue to have storage until main ends, right? So the storage is available throughout the entire program. Similar is thread local. So if you use the thread local keyword, they have thread storage duration, and instead of available throughout the entire program, it's only about the thread. And crucially, there's like a distinct copy per thread. So when we make a thread local, we create like one copy of it when we start the main thread. And when we create another thread, we create another copy. And when we destroy the second thread, we will destroy the thread local copy of that thread, but the main one is still alive. So it's like static just per thread. Now, I said that, for example, for a static variable, the static storage duration, the storage is available throughout the entire lifetime of the program. But this doesn't mean that the objects are, because in general, the storage duration is not the same as the lifetime of an object. Right? The lifetime is a subset of the storage duration, but not necessarily the same. Because the lifetime only starts when two things happen. First, we need to allocate storage, and then we need to complete the initialization if there's any. The good news is that for automatic storage duration, they actually match. There are some terms and conditions that we will explore later on, but in general, when we have a variable of automatic storage duration, when we allocate storage, we also start the lifetime, because at this point, we will perform the initialization if there's any. For static and thread local duration, it's complicated. There are difference between function local statics and global scope. We've got constant and dynamic initialization. There are a bunch of techniques like nifty counters, the module dependency graph, and inline variables. And essentially, I've given an entire 60-minute talk just about lifetime of static storage duration. You can find it at that URL. So I will not go into more details that right here. It's an entirely complicated thing. The second thing to point out is that in general, an object can have its lifetime start without a known value. What do I mean by that? Well, when we allocate storage for an automatic or dynamic storage duration, and we don't put an initializer, and the class doesn't have like a constructor or whatever, then it retains an indeterminate value. And if we use it, that is undefined behavior. So here we create our int without an initializer. this allocates storage, and it also starts the lifetime. Because for an automatic storage duration, we would know when the initializer, but since we don't have any, we're immediately done and start the lifetime. Which means this is undefined behavior, right? Because we're reading a variable without an initializer. It's not undefined behavior because we're using an object whose lifetime hasn't started, because the lifetime has started. The undefined behavior is that we are reading an indeterminate value. We can assign it, and this is, again, the assignment is fine, because we already have an object whose lifetime has started, so we can assign it. And since this does not read an indeterminate value, the assignment is fine. And when we read it further on, it all works out. So this is something to keep in mind. And there's actually some change going on in a future C++ standard. So in C++ 26, this is no longer undefined, instead it's erroneous. And the idea behind erroneous behavior is it's a new kind of undefined behavior, but like a weaker form. So with like undefined behavior, the compiler is allowed to assume that undefined behavior cannot happen and optimize accordingly. With erroneous behavior, there's not a formal spec of erroneous behavior, it's just, but the proposal describes it informally. But essentially, the implementation is not allowed to optimize it out, but it just indicates that, hey, this is an error, and the implementation should maybe terminate the program or do something like that, but not do dangerous optimization. So it's a much tamer form of undefined behavior that makes a lot of code better. Okay. Any questions at this point? So let's move on to new and delete. So an object is created by a new expression. And we're going to see this sentence a lot in the talk. And then we also have a delete expression, and the delete expression destroys an object. And with that, we can sort of manually create our objects. So we create an object here with the new expression. This also initializes it, allocates storage, and starts the lifetime. Then we can use it as before, and then we delete it. Not that we're actually having two objects here. So first of all, the int we created on the heap, and then the pointer to the int that is a variable with automatic storage duration. So the first line actually creates two objects for us. And this is very straightforward. The same caveat applies here, that it's possible to create one with indeterminate values. So this starts the lifetime of an int, but it doesn't give it an indeterminate value. So this is undefined behavior. We have to assign it as before. This is going to be erroneous as well in C++ 26, and so on. And that's new and delete. They are even simpler than a variable declaration because you manually create and destroy the object. So let's move on to something more interesting, temporary objects. An object is created when a temporary object is created, which is a bit of a tautology when you cut the rest of the sentence out. So the idea is here. We have a function f that takes a reference, and then we call it with the value 42. Now the value 42 is not an object, right? It's just a number. But the reference is an alias for an object. So the compiler has to create an object in order to make this happen, because references always have to refer to some object. So we need to create a temporary object in order to make this code complete. And this creation of temporary objects is called the temporary materialization conversion, which is a great phrase for Hangman. And the standard says about it, a PR value of type t can be converted to an x value of type t. This conversion initializes a temporary object of type t from the PR value by evaluating the PR value of the temporary object as the result object and produces an x value denoting the temporary object. That's a lot of words, but what essentially says that whenever you use a PR value where you require an object, we create a temporary object. We've seen this happens when we bind a reference to a PR value, right? References are aliases, so we need to create an object in order to have the alias. And of course, this only compiles for like const references or R-value references. When we do member access on a PR value, right, the member has a this pointer, which needs some storage. And the temporary doesn't have a storage, so we need to create a temporary object, put it in there, and then we can do the member access. When we use an array, so an array really wants to be a pointer to the first element. So essentially, any use of an array PR value creates an array somewhere in temporary storage, puts it in there, and then we can use it. Or the final one, when you have a function that returns a PR value. So let's say you have a function that returns a std string by value, and then you call it and you do nothing with the result. You still want the destructor to run. And the destructor is a member function, so we need to this pointer. So we need to put the PR value somewhere. So we create a temporary object, initialize it with the PR value, call the destructor in order to properly clean it up. So that's why temporaries are created. And as soon as we create a temporary, we also start the lifetime. Interesting is when the lifetime ends. So temporaries are destroyed as the last step of evaluating the full expression. So here we've got the function f, which takes a bunch of references in order to force temporary lifetime creation. And then we have a function g, which returns the PR value. And then we call it with the value 11 and the PR value. So this creates two temporary objects. in order to make the call work. And those temporaries are destroyed in the last step in evaluating the full expression, in other words, at the semicolon. Which is nice because it means that while we're inside f, we have two objects, we can freely use the references. And they're only destroyed after the call to f is returned and we reach the semicolon. Of course, it gets incredibly dangerous if f takes the address of the arguments and stores them somewhere in a global variable or something, because then we immediately have dangling pointers as soon as the call returns. But as long as we don't do that, within f, we're free to use our references. They're destroyed at the last step of the full expression. There are two exceptions to this rule. And they both refer to as temporary lifetime extension. So in the first case is when we bind a reference to a temporary directly, the lifetime is extended to the temporary of the reference. So first of all, a reference is not an object on itself, so it doesn't really have lifetime, but the standard refers to the lifetime of the reference as if it were an object. So in this case, we treat the lifetime of ref as if it were like an object of automatic storage duration, which means that the lifetime of the reference ends at the closing brace. And when we create a temporary, this lifetime is extended in order to match the lifetime of the reference. Otherwise, this code would just be really silly, right? Because we create a temporary object, if it were destroyed at the semicolon, we immediately have a dangling reference, which just wouldn't help anybody, right? So the standard somewhat helpfully extends the lifetime in order to make this well-formed. But it's not really that helpful because it's like really fragile. It only works when we directly bind a reference to a temporary. So let's say we have a function getStrings, which returns a vector of string. And the first time we're binding that result to a const auto ref. This triggers temporary lifetime extension because we have a PR value that we bind to a reference. So we materialize an temporary whose lifetime gets extended to match until the closing brace. In the second case, we bind that to the reference to like the first call of getStrings, like the array subscript operator. And here the temporary is actually created in order to call the array subscript operator because that's a member function. And then the array subscript operator returns a tref. So we don't bind the reference to a temporary. We bind the reference to a reference that is returned from a function who's called on a temporary. So we don't trigger temporary lifetime extension, and we just immediately have a dangling reference as soon as we reach end the line. Right? Only if you directly bind a reference to a PR value do we get temporary lifetime extension, and not if you do it indirectly by returning a reference derived from the temporary object. So you have to be incredibly careful when writing code like this, and essentially you shouldn't rely on temporary lifetime extension in this case. The second case of temporary lifetime extension is a lot more useful. So when we have a range-based for loop, like after the colon, we can create a bunch of temporaries, and they're still alive until we exit the for loop. So which means that when we write code like this, where we iterate over the functions returned by getStrings, this is perfectly fine. The temporary gets created, and it will be destroyed after the loop. And crucially, this is also fine. So here we're iterating over the first string, which triggers the creation of a temporary. But the lifetime of all temporaries created will be extended until the end of the for loop, so it will only be destroyed at the end of the for loop. And this used to be not fine until C++23 or 20, but like thanks to Nico, this got fixed. So now we can just use the range-based for loop without having to worry about temporaries. Yes?
I don't think all the compilers have changed it yet.
Oh, yeah, okay, so the comment was that not all compilers have changed it, yes. I'm not talking about compilers, I'm talking about the C++ standard. I don't care what the real world does.
That's already mentioned, but when does the lifetime start of the different arguments going into the function?
Right, so the essentially lifetime starts when we create the temporary in order to bind that to the reference, but it is not specified in which order the arguments are evaluated. But again, this is like, I'm focusing on the lifetime part, and like this is like a different problem. I'm just ignoring it, right? There's a lot of rabbit holes we can go into, but then the talk would like, are you doing anything over lunch? Because otherwise I'm happy to. So that's the safe form of temporary lifetime extension, and it just means basically you can just use for loops, provided the compilers implement the standard, which was sort of my assumption here, then just works fine. Now let's get to the interesting part. Placement new. An object is created by a new expression, and there's a special kind of new expression, placement new. It essentially is an explicit constructor. So if you have some memory, you can call placement new in order to create an object in that memory. And this will then give you a pointer to the int we've just created in that memory. Now, when calling placement new, you have to be a bit careful because placement new can be overloaded. You can write your own version in a different namespace, or you can write one that takes like an int pointer instead of a void pointer. So when you want to call the actual placement new, you always have to like qualify to call the one in the global namespace, and always have to static cast it to a void pointer. Otherwise, you might call some user-defined overload, which is fun. So there's a convenience function in the standard to construct add, which essentially does that. So in real code, I recommend always calling std construct add. It's even const explorer, whereas placement new is only going to be const explorer in C++26. Even though this is literally the implementation of construct add, it's just the compiler doesn't like it if you use placement new outside of a function at compile time that's called construct add, which is kind of fun. But anyways, I'm not going to be using construct add in the slide code because it doesn't fit on the slide. It's a bit more typing at some parts, so but like keep that in mind. You should use construct add in order to avoid the dance of doing the global qualification and the static cast. So placement new manually calls a constructor, which means we can manually start the lifetime for objects, and then we manually need to destroy the object by explicitly calling the destructor. Now, there's a bit a fun quirk about the syntax here. So the syntax is like dot tilde identifier, which means that it does not allow built-in types. So you cannot write dot tilde int because int is not an identifier. Simply the grammar doesn't allow it. And you also can't write dot tilde std string because std string is not an identifier. It's like a qualified name or whatever. So what you have to do is like either use like a type def, to like type def int to like int underscore, and then you can write dot tilde int underscore, or you can call std destroy add, which takes a pointer and calls the destructor. And this is like purely a syntactic. So even if t is an int, we can still call the destructor that way because in the grammar we don't write int, we write t, which is a regular identifier. So this is just a very weird syntax quirk that you have to keep in mind. C++ is such a bizarre language, but you know, just what we do. So we can use placement new to like create the object and then manually call destroyer to destroy it. But the question is, how do we get memory without any objects already inside, right? Well, and for that we can use various functions. The first one is obviously malloc, right? So malloc just allocates storage. So we say we allocate storage for an int, then we start the lifetime by initializing an object in there. Then we can use it. Then we can end the lifetime by calling the destructor by destroy it, and then we deallocate the storage. And with that sense, we sort of like manually implemented the entire life cycle of object creation. We manually allocate storage, manually start the lifetime, manually end the lifetime, and manually deallocate storage. So if you want to do everything by hand, you can. A bit more C++ version is to call operator new. So operator new is a global function with a weird syntax, and just like malloc, it just allocates storage. And then just like malloc, we have to like start the lifetime, use the object, end the lifetime, and then deallocate the storage by calling operator delete. Every time we create an array of unsigned chars.byte, this allocates storage for objects. So here we have a buffer that is suitable aligned for an int and suitable big for an int. And this allocates storage that we can then placement new inside. And then we can use it, call the object, and like the storage gets deallocated automatically because it's automatic, so we don't need to worry about it. A more interesting case to get storage is that we can actually reuse the memory of an existing object. So here we've got an int. We allocate storage for it, we start the lifetime, we've got our int. We then end its lifetime. This is okay, because now we essentially, like we still have x, but x doesn't refer to anything, like it's just the shell of, here there used to be an object there. And then we can call placement new to create a new object in the space, and immediately start the new lifetime. And then we can use it, right? And then this ends the lifetime. There's something weird going on here, because like we end the lifetime of which object exactly? Like of x, but we've destroyed x already. So what's going on there? We'll look at that later on. Let's look at some other words first. So when we reuse memory in this way, we have to be really careful. So for example, creating a new object within the storage of a const object is undefined behavior, because const means const. So when we got a const int and we end the lifetime, this is actually fine. We just cannot call placement new into it. This is undefined behavior because const means const, and we could sort of change the value of the const object by that if we do that. So const means const. Most of the times. It only applies to objects of static, thread, or automatic storage duration. So if we allocate a const int on the heap, we can actually change its value by like placement newing something in there. Because const on the heap just doesn't matter. Which is kind of fun. Also note the destructor still runs. The compiler doesn't care that we manually destroyed it first. So when we create, for example, a variable of automatic storage duration, and then we will destroy it, we end the lifetime, and then the compiler will end the lifetime again. And this is undefined behavior because we're calling the destructor twice. Right? We have to be careful to put something back in after we destroyed an object. So let's get back to this example. So we create our int, we destroy it, we create a new one, we use the pointer. Is this okay? This is okay because we just used the pointer. The question is, what about this, right? Can we still refer to the original x? Because we destroyed it, right? X doesn't exist anymore. Can we still do it? And the answer is, it depends. So, after the lifetime of an object is ended, a new object is created. A pointer that pointed to the original object, a reference that referred to the original object, or even like the name of the original object, will automatically refer to the new object if and only if the original object is transparently replaceable by the new object. So sometimes we can still use x, or pointers, or references, whatever, to x after we replaced it, but only if it's a transparent replacement. And essentially, a transparent replacement means that A is transparently replaceable B if they're on the same storage, obviously, and they have the same type, ignoring CV qualifiers. So we can replace an int by an int, but we can't replace an int by a float. This is not transparent. And then there are some caveats about like const objects and base classes and no unique address members, which are kind of weird, but we don't need to get into that. And then there's some another caveats about like when we replace the sub-object of an object, it goes recursively, but yeah, it's not important. So what this means in practice is this is a transparent replacement, right? We're replacing an int by another int at the same storage. We're not in one of those weird edge cases, so we can still use x. Because x automatically will refer to the new object, no longer the old one. Yes? When would you use this? That is an excellent question. So, we can replace transparent objects. I don't know. I mean, I do know there are some cases like when you implement optionals or whatever, or by like in the implementation of containers. I'm just going over the woods. Yeah. So if the destructor still runs at the end of the scope, destroy it, runs it again. So like destroy it, just runs it first. Right? So we destroy the int, like we destroy an int, then we create a new int, and then the compiler destroys the int at the end of the scope. Yes.
Can we just press second call for the destructor?
Is that no, not with an automatic storage version. If you put it on the heap and then you just go and delete, but like the compiler will automatically destroy it, so you kind of screw it there. A more interesting case is something like this. So in the assignment operator, we can sort of like transparently replace this with something else. So we destroy foo this, then we create a new one, and this is transparent replacement. So this means okay. And sort of it's still not a good idea because like if foo has like no unique address members, or foo actually is a sub-object that is created no unique address, there are a bunch of bugs you can get into. But like if you know how foo is used, you can implement the assignment operator that way. It's not technically undefined behavior. It's still a bad idea because it can very easily become undefined behavior because you don't know who's going to be embedded into other objects. But other than that, it's fine. I'm not giving like practical guidelines on how to write code. I'm just going over the rules here. So yeah, I don't have use cases for a bunch of the stuff. I just wanted to mention them. Right, and similarly, like we can do that for the X member here. We can destroy it and transparently replacement, and everything works fine because essentially, like nobody cares that we did transparent replacement. Now let's get back to the example where we transparently replace a constant. It has to be on the heap because remember, const is const unless it's on the heap. So we can do a non-transparent replacement here, which means that we have to use the new pointer that we get from placement new and not the old one. If we use the old one, that is undefined behavior because we have non-transparent replacement. And the reason behind that is the compiler sees, well, pointer points to a const object. So star pointer cannot change because it points to a const object. So I will keep using, just optimize the star pointer to like 11 because it points to a const object which cannot change. And when we changed it, essentially we cannot use the old pointer anymore because the compiler assumed that it does not change. This is why it's not transparent. This is why this code is undefined behavior. But we can fix it. We just have to call like the favorite standard library function launder. Launder is a magic identity function. It takes a pointer and it returns a pointer, but it makes code okay. So if you launder the pointer, this is fine because essentially it tells the compiler, hey, pointer might have been non-transparently replaced, so you actually have to dereference it again to get the correct value. So if you launder a pointer after a non-transparent replacement, we can use it. Launder even helps if you use references. So now we're having a const ref that we bind to the object on the heap. then we do non-transparent replacement using the reference's undefined behavior, but taking the address of the reference, laundering it, and dereferencing it is fine. Because we have the pointer to the wrong object, but then launder magically makes it okay. Now we're going to look at launder in more detail later on, but like it does not prevent undefined behavior in all cases. Like let's say float and int have the same size and alignment, and then we create a float object in the heap, we destroy it, we put an int object in its place. We can read the int object because that is fine, we've got an int there. We cannot read the float object because we don't have a float, right? We've just destroyed it, we put an int in there. And even if we launder it, this is still undefined behavior because we still don't have a float, right? Launder doesn't help you with that. Launder only helps you if you do non-transparent replacement. We will look in more detail later on, but it doesn't help in this case. It only helps in the previous case. You still need to actually have an object of the type the pointer expects in there. It's not a magic get out of UB free card. Now, you might ask, when do I need to use the launder? Well, when you want to reuse the storage of const heap objects, because remember, you cannot reuse the storage of other const objects, base classes are now unique address members. In other words, never, right? Because when would you want to do one of the things? I want to point out that originally the rules were much more strict about like what's a non-transparent, what's a transparent replacement. And so they were actually, when launder was introduced, there were like actual real use cases that came up where you had to use launder. But the standard is that relaxed the rules, made more transparent, so basically never have to use launder. Although we will come back to that. Any questions about placement new? Okay. So let's talk about implicit object creation. An object is created by an operation that implicitly creates objects, which again is great tautology. Doesn't tell you anything. The idea is the following. This is like C-style C++ code. We malloc an int, and then we immediately deformat it to assign it a value. And under all rules I've presented so far, this is undefined behavior, because we don't have an int object, right? We just allocated storage for one. So the assignment should be undefined behavior under the rules. But like in practice, it really shouldn't be undefined behavior because people write this code. Like all C programs look like this, right? So this should not be undefined behavior. And until C++20, it simply was undefined behavior, but like nobody cared. Until like the standard decided to fix that and make this well-formed by introducing the idea of implicit object creation. So the standard specifies some operations at implicitly creating objects and starting their lifetime of implicit lifetime type. If doing so would mean we suddenly have defined behavior. In simplified words, if it helps you, the compiler creates objects for you. And this is the only instance of the C++ standard where the compiler goes out of its way to avoid undefined behavior for you. Like in all other instances, it will just hit you in the back of your head. But like in this case, it will actually catch you and prevent. Yes? That's 20, Jason. Yeah. I purposely don't put the C++ standard on there because as we reach this level of the point, like so much is in flight and so much is going to change. So I'm just going to present whatever is the collective understanding of the committee at any point, and the rules are always in flight. So if it helps you, the compiler creates objects for you. They have to be of implicit lifetime type. This essentially means that like they're scalar types or class types. Essentially, construction and destruction do nothing. Right? If you have a constructor, if you have a destructor that actually do something, they're not implicit lifetime types, then compiler cannot implicitly do side effects, as we will see later. So which of those operations implicitly create objects? First of all kinds of allocation functions, including malloc. So crucially, this code is fine, because the star pointer would be undefined behavior, but malloc implicitly creates objects, so that the compiler will implicitly create an int in order to make this code well-defined. That's sort of the rule there. And the same thing applies to operator new, allocator allocate, and some other allocation functions like reallocate stuff. Yeah.
Create something using a size of and a line of that have the same.
Okay, so how does the compiler know that it should create an int? We will look at that later. But for now, it is allowed to create an int, and creating an int would make it well-formed, so the compiler somehow knows to create an int. When we have anything that starts the lifetime of an unsigned char array implicitly creates objects inside that buffer. So we've got an unsigned char buffer, we create an int pointer, and then we use it, and this implicitly creates an int, and this is fine. Except for a bug in the C++ standard, because the reinterpret cast to the int pointer actually doesn't give you an object a pointer to like any objects created inside the buffer due to some oversight in the wording. So technically, we have to use .launder. Please pretend this .launder isn't there. There's a proposal in flight that makes this unnecessary. There's just some wording missing in some other place. But I don't want to like put invalid code on the slide. So I need to write this .launder for now. Eventually, the launder disappears and it just works as intended. It's really just a bug in the standard. Some wording is missing. So when we have an unsigned char buffer and we reinterpret cast it in a future version of C++, we can just use it directly as the object because we implicitly create objects in there. Memcopy and memmove also do that. So here we have a char buffer. A char buffer is not an unsigned char buffer. It's also not a stored byte buffer. So this on its own is not allowed to implicitly create an object. But when we memcopy an int in there and then later use it as the int, and again we need the launder because of the other thing, pretend the launder doesn't exist, the memcopy is allowed to create the enforce to make the code well-formed. So memcopy and also memmove implicitly create objects in some storage in order to make the code well-formed. And then there's a set of implementation-defined operations that do that, like presumably mmap or virtual alloc or whatever, right? That also implicitly create objects, just like malloc or the other allocation functions. Now, the question was already raised, how does the compiler know to create an int? And the answer is the compiler uses time travel. So let's say an int and a float have the same size. We create a buffer that is big enough for an int or a float. And then we figure roll the dice. And if it's like even, then we create an int. And if it's odd, then we create a float. Now, at this point, again, the launder, because of the other thing, pretend the launder doesn't exist. But let's say it's even, so we're about to assign an int in there. At this point, the implementation needs to travel back in time to the line where we created the buffer and create an int in there in order to make the code well-formed. And similarly, if we pick the other branch, the implementation travels back in time in order to create a float to make the code well-formed. Now, of course, I'm not a compiler writer, but I don't think like time travel is implementable, which means that it's purely like a thing in the C++ standard in order to make the semantics well-formed. Because it's the abstract machine can do time travel to make it well-formed. And it also means that the constructor cannot have side effects, right? Because we cannot actually execute the side effects at the appropriate amount of time because we can't do time travel. And it is actual time travel. So it's not like, okay, so once we like say, okay, it was even, we put an int in there. If we then later on use it as a float, the compiler isn't gonna suddenly go back and create a float in there. No, as soon as we create an int in there, there's an int in there. There always has been an int in there, and this will not change because we time travel back to put an int in there. Alternatively, you can use it like quantum mechanics. So like when we create the buffer, it automatically like it creates an int and a float, and then the wave function collapses as soon as we observe either one. It's like pretty bizarre semantics, but it just works out to make it well-formed. So it doesn't matter whether how you malloc the thing, like because that isn't important. It's just like the first use travels back in time in order to create the objects in there. And from that point on, there always has been an object of the appropriate type. Now, just like launder, implicit object creation does not prevent undefined behavior. So if we just have an int and we just interpret cast to a float, this is still undefined behavior. Right? Because the reinterpret cast isn't the operation that implicitly creates objects. It's the other set of operations. Right? The reinterpret cast just triggers the time travel to go back to the other place to create the object. But here the compiler cannot create an object implicitly because we don't have one of those magic operations. So this is still undefined behavior. Questions? Yes?
Yeah, can you allocate for like a buffer of like 10 minutes? So like allocate for one allocation and when do I arithmetic first 10 are 8?
Yes. Yes, that is possible. So you can, like, if you just get a big byte buffer and you start using the first couple of bytes as ints, and then do pointer arithmetic, and then you start using the rest as floats, the compiler will travel back in time to create the int and the floats when creating the buffer. You just have to be careful with the pointer arithmetic. So, like, when you when you do int pointer arithmetic, you cannot go to the place where there are floats because the int arithmetic is only valid in the place where the compiler has created the ints, right? So you have to do pointer arithmetic and the bytes, advance it first, then use something that triggers the creation of ints, and then use the already advanced pointer to create the float. Right? If you advance it further, you're still iterating over a byte array, but there are no ints in there, so you can't do pointer arithmetic on the byte array. Right? Yeah.
So you can do time travel thing on the same like location that have the first of the internet.
Yeah, so if you use the same location, so the first access that is undefined behavior triggers the time travel, and then all subsequent accesses, because let's say that creates an int, and then you later access it as a float, and that is undefined behavior. This does not trigger time travel again, because we already did it. Like, this is then just undefined behavior, because you have an int. There always has been an int. Like, there was no point where there wasn't an int in the buffer, right? And so it's... Okay. So let's say we want to do something like this, right? We've got some bytes coming in from the network, and we want to interpret them as destruct, right? This is a pretty common thing. We're doing all the good thing by using launder, whatever, we don't know where the thing is. And like, depending on how we allocated the buffer, this might be undefined behavior, right? If the buffer came from malloc, it's fine, because malloc implicitly creates objects. I mean, we might read like uninitialized data, but apart from that, the object creation works. But if the buffer came from like an operation that does not implicitly create objects, this might be undefined behavior, because we don't have anything to travel back to in order to implicitly create objects. So this might be UB depending on how the buffer came from. And this is a bit bad, because we want to like monitor this in isolation and ensure that this always works. And you might say, okay, let me just use placement new then, right? So I placement new the struct in the data. And this code is now well formed. But even though data doesn't have a constructor, so the placement new doesn't actually do anything, it semantically does something, right? It starts the lifetime of an entirely new object. And when we do that, we don't get any properties of the old object that may have been there, including the value. So even though it does not actually change the value at runtime, it logically changes the value. So we don't have any guarantee that it still contains the same value as it would have before the placement new. So this actually, like, in the abstract machine, it changes the value. On the actual CPU, it doesn't care, like it doesn't do anything, but like in the abstract machine, it changes the value. So this is well defined, you just don't get the values you wanted. Yes?
If there was a value before, you don't do explicitly every side before we actually...
I will get back to that. Yeah. So what we want to do is we want to create a new object, like we just want to say to the compiler, hey, please implicitly create objects in there if they aren't already, but don't override the values. And the spelling isn't placement new, the spelling is start lifetime as. So start lifetime as is another magic standard library function, just like launder. You give it a type, you give it a pointer, and you say, hey, please ensure that if necessary, start the lifetime of the object in there. There's also a version that takes an array.
What's special about char? Because obviously you've said when ints are in, but with chars it seems purely.
So yeah, so first of all, it's an unsigned char array, and that's important. Right? It doesn't apply to char arrays in many cases. It applies to unsigned char arrays. And what's special about them is some wording about unsigned char arrays implicitly providing storage for other objects, which has consequences for some stuff. I will explore that in more detail a bit later on. There are also a bunch of bugs there, but like unsigned char is like sort of special to like create byte arrays. Crucially not char, because of some interesting wording conflicts. So they got rid of char was accidentally dropped in some place. It's a bunch of fragile stuff in there, yeah.
Data had a default member initializer.
Yeah.
It wouldn't be an implicit lifetime.
Exactly. If data would have an implicit, it wouldn't be an implicit lifetime type, and then we can't do the time travel, so we don't implicitly create objects, and we cannot call start lifetime as.
This would be UB, right?
I think start lifetime as doesn't compile.
Okay.
For, but like it would be UB without like in the other operations, because right. Okay. And so start lifetime as is sort of a magic standard library function, but we can implement a subset of it actually before formed already ourselves using mmove of the pointer to itself. Because mmove implicitly creates objects, right? So when we memcopy the bytes to themselves, we don't do anything, but we have the side effect of implicitly creating objects if necessary. So now we've got an operation to time travel back to in order to create the object of the appropriate type. And then we still need the launder depending on how we derive the pointer. The standard implementation is probably just a compiler built in, and it also works for constant stuff. So even though mmove doesn't actually copy anything, it might still do like self-assignment, and this would then break for const or whatever, right? But like we can approximate start lifetime as with a mmove, which isn't useful to now. It's just kind of fun fact. So there was a comment about like, okay, so we call placement new on on storage that already has objects in there. Don't we need to destroy the objects first? The answer is no, because there's also implicit destruction of objects. So the lifetime of an object ends when we call so for class type, when we call the destructor, and when T is a built-in type, then the object gets destroyed. It's a weird distinction, but essentially when we call the destructor, also when we release or reuse the storage. So when we've got, right here. So when we've got an int object, I can call placement new, this reuses the storage for a new object, so this automatically ends the lifetime of the first int and starts the lifetime of the second int. Similarly, when we've got an unsigned char buffer, this actually starts the lifetime of an unsigned char array. And when we then call placement new, that ends the lifetime of the unsigned char array and starts the lifetime of the int. And now this reuse or release of storage, this doesn't actually call the destructor. Right? It just ends the lifetime, but it ends it without calling the destructor. So this might need to leak to memory leaks, right? Because we just reuse the storage, we end the lifetime, but we never call the destructor. But memory leaks aren't actually undefined behavior. So we have a std string, and we reuse the storage. We don't call the destructor, so we leak some memory, but this is perfectly fine, right? It's not undefined behavior, it's just a memory leak. The standard's fine with it. And then when the destructor runs, it will actually destroy a new string object because of transparent replacement. If we were to do like a non-transparent replacement here, we would have undefined behavior because the compiler still called the destructor on the original object. Answers that your question? Okay. Any other question? So let's talk about provenance. I have a function do something which takes a pointer, and then I have a function foo which creates two objects, x and y. We set y to 11, and we call do something with the address of x. And then we return y. And compiler is going to optimize each function in isolation. So we expect this one to optimize that to return 11, because we set y to 11, then we don't change y, right? And so we just optimize that to return 11. But what if that is the implementation of do something? Do something takes the address passed in, adds 1 to it, and sets that to 42. Let's say that's the implementation, and it just so happens that that is also the address of y. So the address of x plus 1 is the address of y. Then we would change y, which would break the optimization. So this has to be undefined behavior, otherwise the optimization wouldn't. Which is fair enough. The more interesting thing is what happens if we do this. So let's say the address of x plus 1, if that is actually the address of y, then we call do something with the address of x. When we then do the pointer arithmetic, we reach a pointer that is bitwise equal to the address of y. So we are allowed to modify it, right? Because we have the same pointer as the y, right? We just got there by a pointer arithmetic. And then we set that to 42. And can we optimize, this still breaks the optimization. So either the optimization isn't allowed, or we're doing something weird here, right? Because the compiler does not see, optimizes each function in isolation. And do something on its own is fine. If that is an array, this is perfectly fine. If pointers passed in an array, this is fine. So something is going on here. And the something is going on here is the following bit surprising fact. Just because two pointers are equal doesn't mean they point to the same object. So even though two pointers are equal, the equals returns true, memcomp returns true, they have the same exact address. They're not interchangeable. They don't necessarily point to the same object. And this is because of something called provenance. So provenance isn't a term in the C++ standard, it's a term optimizers use. The C++ standard uses the concept of safely derived pointer values, which is a bit more confusing. Provenance is a simpler mental model for this. So a pointer is logically, on the abstract machine, a pair of address and provenance. The address is the only thing that's physically observable. That's the thing the CPU cares about. That's the one that's being compared when you do memcomp or equals. And then the provenance is sort of a history where the object came from. So it identifies the object or location the pointer was derived from. And when we dereference a pointer, this is only valid if the address is in range of the allowed addresses for that particular provenance, and the current provenance at that address is still the same as the provenance of the object. And crucially, pointer arithmetic does not change the provenance. So here, we do pointer arithmetic x plus 1. This produces something whose address may be equal to the address of y, but it doesn't have the provenance of y. It still has the provenance of x. And by having the provenance of x, the dereference is undefined behavior, because that address is not the address of x, right? It's the address of a different allocation with a different provenance. So this is undefined behavior because the address is not in range, and this explains why the compiler is allowed to do the optimization. Because since nobody, the address of y is never taken outside the function, nobody can get at the address of y to modify y, right? It just simply isn't possible because of the provenance changes. And provenance also explains a bit of what's the launder. So when we have our heap object, this is provenance A. We then destroy it, we place a new one in its place, and the resulting pointer is provenance B. Then we can dereference new pointer, because at this address we have an object of provenance B, and we're dereferencing it using a pointer of provenance B. But we cannot dereference pointer, because pointer is provenance A, and we now have an object with provenance B. But when we launder it, launder, essentially all launder does, it updates the provenance. So we give it a pointer to the address of provenance A, and it returns a pointer with the same address, but now it has the correct provenance of that address. And so with std launder, we sort of update the provenance. So it's an identity function on the hardware, but like logically, it changes like to the second part of the pointer. It updates the provenance to the correct one to make it fatal. Crucially, launder cannot be used to make this example well found, because the precondition is that like of launder is that like you still have an object in there, and when you do the pointer arithmetic to the past the end object, this is not a valid pointer for the underlying allocation. So you cannot use std launder to get out of this mess. Only in this case, where we actually like we have a pointer that still points to like a dereferenceable address based on that original provenance, and then I can update it. Yes. Mm-hmm. Yeah. Yeah, so std launder doesn't modify the pointer in place. It returns you a new pointer, right? So you could say like pointer equals std launder pointer, and then it's fine. But like it's like it takes the pointer by value, so it doesn't modify the pointer, and like essentially the second field, the provenance fields, cannot be changed. Yes.
How does this pointer arithmetic differ from something like std copy, where you are implementing a pointer copying values from one thing to another?
Do you mean copy or mem copy?
Well, any function that fits in that does pointer arithmetic.
Right. Right. So you've got like pointers begin and end in an array. All objects in an array have the same provenance. So you can use pointer arithmetic to go between them. References also has provenance, which explains this example, right? So the reference has the provenance of the old object, so we have to launder it to get the reference of the correct answer. So provenance is a bit of a sticky property. It can only really change by a certain version. So like each object has a unique provenance. All objects in an array have the same provenance, so you can do pointer arithmetic between them. And reusing the memory of an object changes the provenance unless we do transparent replacement. And then all launder does, it updates the provenance of an object, but crucially, pointer arithmetic on its own does not update the provenance. So pointer arithmetic is only allowed within an array, because then we've all got the same provenance. Okay, questions about provenance? So let's look at type panning. Again, we're assuming that int and float have the same size and alignment. We create our int. We take the address of it. Then we reinterpret cast that to a float, and then we use it. Now, this code has undefined behavior, and because of the strict aliasing rule. And colloquially, we say that you can't reinterpret cast between unrelated types, but that's actually not quite correct. The reinterpret cast is perfectly fine. The problem is the access. So if a program accesses an object to something whose type is not similar to some other thing, that is undefined behavior. So in this code, the reinterpret cast is perfectly fine. The dereference is the problem. In other words, the type of a pointer or reference absolutely doesn't matter. It's only relevant when you actually do an access. So here, we don't have any strict aliasing violations, because even though we sort of like have the same address and whatever, we create the lifetime of an object in that memory. So we can dereference the pointer because we access an object of the correct type. Like we have a float object with a pointer to a float object, this is fine. But it's not type panning because we can't use the I anymore, because I now refers to is at the location, but the location there's no float object, not an int object. This violates the strict aliasing. Alternatively, we could do start lifetime as. This can actually be used for type panning because it doesn't change anything. So we say we start the lifetime of the float at the location. So this doesn't change the values. It just creates a float object. So now we can use dereference the float pointer because we actually have a float. But of course, we can no longer use the int because we now have a float in there and not an int. And you have to be like really careful about how you actually get the pointer. So like we reinterpret cast our float to our int pointer to a float pointer first. Then we do the placement new. And then we dereference the float pointer. So at this point, we're having a float pointer whose address points to some location of memory where we actually have a float. But we're still not allowed to dereference it because that float pointer still has the provenance of an int. Right? So it still refers to an int pointer even though its type is float, and as the memory location we actually have a float, like we still can't use it because it's not the correct float. Right? We have to like, yeah, and similar thing is we do the reinterpret cast after. It doesn't matter because like the f pointer still has the provenance of an int, even though the type is float, it actually points to an int. So we cannot dereference it because we don't get the int pointer. We have a different provenance, right? We have to like either use the return value of place menu in order to get a pointer with the correct provenance, or launder it. And this is like a really weird, subtle distinction. But it's just a consequence that like the type of a pointer doesn't matter, and also the address, also the provenance needs to match. And when we do a non-transparent replacement, as we do here, the provenance changes. So we cannot use any old pointers, even though they have the correct type, already point to the correct address. We just can't use them. We have to launder them. Yes?
The start lifetime as. Can you
Yes?
start the lifetime now again as a being to use the I again or
Yes, I have that exact example later. Yeah. And this sort of behavior that like you have to be careful on how do you get the object in order to use it, and you might have to use launder, also explains why this is undefined behavior under the current wording of the standard. When we've got an unsigned char buffer, even though it wants to implicitly create objects in there, the pointer we get is still a pointer to the unsigned char buffer and not a pointer to the instance side. And this is a bug in the standard, right? This is just supposed to work, but currently we have to use launder in order to get the pointer to the actual int that would be created inside that buffer. And this paper fixes this. I'm just going to pretend that this is going to be merged because it's obviously going to be merged. I mean, never say that, but you know, it's just weird that like, otherwise the unsigned char exception is just completely useless because we can't do anything with it. So, final use case for launder when you want to reuse memory as the storage for a different type. Which is still like never, but like there are some terms and conditions that may apply. Now there are some exceptions to the strict aliasing rule. The first one is the unsigned char byte exception. So even though we don't have, so the first one is you got an int, you get a pointer to an unsigned int, we can dereference it because like it's the unsigned version of the signed thing. Like this is a weird exception, it's just fine. Like even though we don't have an unsigned int, we just have an int. For all other types, this would be undefined, but there's an exception here. And then the second is we can use anything, like reinterpret anything as a char, unsigned char, stored byte. And like this is the only case where like char is still special and not just unsigned char, stored byte. I don't know why like we don't treat char the same as unsigned char everywhere else, but you know, it just happened. And then we can do that. And the idea behind the last one is that we can use it to access the object representation, right? So we can sort of iterate over the raw bytes of an object. And without the exception, this would be undefined behavior because we don't have bytes, right? We have got an int, so we can't dereference a byte pointer. But with the strict aliasing exception, this is fine. Except for another bug in the standard, because the way pointer arithmetic is specified, it requires an array. And the way the wording says, we don't have an array. So we cannot do any pointer arithmetic here. It's just some oversight in the standard. There's another paper to fix it. It's incredible how many just like holes you discover when you prepare a talk like this. So this is meant to work to interpret the object representation, but it accidentally became undefined behavior in C++20 when some unrelated wording was changed. It's a bit fragile, but you know, now you know. So like type panning in general, we want to interpret the bytes stored in one object as an object of another type. And there are various ways we can now do that legally. Right? So as we can see, we can use start lifetime as. So the simple reinterpret cast is undefined behavior, but if we start the lifetime as a float, this doesn't change the value, but now we actually have a float. So we can use it. However, you can no longer use the old thing, right? Because we no longer have an int. And even if you then start the lifetime with an int again, because we're doing two non-transparent replacements, this doesn't mean that transitively we did one transparent replacement. Because we have an int, we put a float in there, this changes the provenance, then we put another int in there, this changes the provenance again. We don't get the original provenance back. So while this works, while we can do that, we can no longer use I. We have to use launder. because I still refers to the original int before we did the two replacements. So it's not a nice way to do type panning, it's a possible way. We can also do type panning by mem copy, and here the idea is that this doesn't mess with objects at all, right? We have an int object, we have a float object, we just copy with the byte symbol. And like this doesn't change the lifetime of anything, so we still have an int, we still have a float, we can use both. They just have the same bitwise values. A fancier version of that is bitcast. It's just a context by mem copy. So we can bitcast it. And again, this has nothing to do with lifetime because we have two separate objects. We don't have to worry about those rules here. And then we have this weird thing. So we have a struct who has an int as a first member. And we take a pointer to the struct and we reinterpret cast as an int. And this is okay. This just gives you the value of the first member. And similarly, we can use the pointer to the first member and get back to the struct. And that is because of an exception in the standard about pointer interconvertibles. So if two objects are pointer, they have the same address and also the same provenance, and we can reinterpret cast between them. And like here are some rules. So like if they're the same object, then they're interconvertible. If one is a union and the other is a member, we can convert a pointer to the member to a pointer to the union. And the example we've just seen here, so we have a struct. We can convert the pointer to the first non-static data member to a pointer to the rest. And then the thing is transitive. And this exception allows this code. So essentially, when we do the reinterpret cast, we implicitly like get a pointer to the correct member. We can't do that with like weird pointer arithmetic to get to the second member. This only applies to the first member. So there's a special exception for this particular case. And without it, this would be undefined behavior because we're having an int pointer that actually points to the A object, but because of the pointer interconvertible rules, we actually have the int pointer to the first member. And just for bonus points, the thing about the unsigned char buffer, where we can't get the pointer, the proposal adds like an extra clause here. So if an unsigned char buffer, it's interconvertible with any objects created in there. Yes?
Since the union and the other is A, not particularly the member of the union, does that mean does it have to be the active member or any member of the union?
Any member of the union.
From the union that I put it there to the union and back to the building without that.
Yes, but you can't dereference that pointer unless it's the active member, right? You just can't get a pointer to it. And then you have to make it active and then you can use the pointer. So union is the final place to do type panning and also the final place where objects are created. So when you implicitly change the active member of a union, this creates additional objects. So we've got the union. First it's an int. We then change this to a float. And now we can access it as a float. This is okay because we implicitly created a float in there. But if we access the int again, this is undefined behavior because we don't have an int. We have a float at that address. So type panning via union does not work, unlike in C. Because in C we do a bunch more time travel. There is one fun exception here, which is the common initial sequence. So we have a union, and they have two structs, and those two structs start with the same sequence of members. Then you can access the common members with either one. So here's the example. We've got a union, we've got two structs, and they both start with an int, the prefix set. And then we can write u.a.prefix or u.b.prefix, no matter who's active, because they both have the prefix member. And this doesn't do any weird stuff about lifetime. It essentially means that, so currently A is active, so when we write u.b.prefix, the compiler thinks, this is undefined behavior, but I can rewrite it to write u.a.prefix instead. So it just does the correct access in either case, and that way we can do that. It's like really common if you've got like an enum, like a union with like the enum tag, you can put the tag as the first member in each one, and then you can just access it regardless of which member is active. So that's type panning.
Time to finish up.
I was promised I have 75 minutes.
75?
Yeah.
60.
I was told I was at 75.
Double check for you.
I mean, I will continue talking in the meantime. So, I mean, yeah, it'll be fun. So this is fun. Invalid and zombie pointers. So, this clause, like before we do something, any pointer can only be used in limited ways, and any reference to the object may only be used in limited ways. So here we've got the int, we immediately destroy it. All of this code is fine, because we don't really access the int. We just create a bunch of pointers and references to it. But all of this code is undefined behavior because we actually access the int, right? And this seems straightforward, right? Because we don't have an int, we can't access it. So we can't access the value because we don't have an object. We can call a non-static member function because it requires like my dereference to this pointer. We can't delete the object because we already did it, right? Or anything with virtual-based classes or dynamic classes. More interesting is this case. So this refers to pointers that point to storage. So after the storage has been allocated, but before the storage is reused or released, right? So there's something about the storage that has to be valid here. And so when we deallocate storage, all pointers that still point to that storage become invalid pointer values. Indirection is undefined behavior because of the previous rule. Deallocation is undefined behavior for obvious reasons, and anything else is invalid, is implementation defined. So using a pointer to deallocate the storage in any way is implementation defined, which might even mean it can trap. So this has fun consequences. For automatic variables, the dereference after destruction is undefined behavior, but the comparison with null pointer is fine, right? You have a pointer, we destroyed it, doesn't matter, it's fine. But if we put the thing on the heap and we delete the pointer, now the comparison with null pointer is implementation defined because pointer points to deallocated storage. And crucially, this might be true. Right? An implementation may choose to like put pointers to null pointer after you've deallocated the storage. No implementation does it, but they're permitted because it's implementation defined what exactly is an invalid pointer value. And this has a pretty fun consequences for like multithreading. So this is a singly linked list, right? In multithreaded, and we want to push something to the top. So we've got this compare exchange loop. We load the old top, we set the new node to the old top, and then we do the compare exchange loop. And we also have pop all, which just removes them all. So something interesting can happen here when we use multiple threads. So let's say our list initially top points to node 1 at address A. That one goes ahead, allocates node 2. It's at old top to node 1, and node 2, next node points to node 1. So far, so good. Then, because it's multi-threaded, it gets interrupted at the worst possible time. Another thread gets along, executes pop all, and deletes node 1. Because that's the only node currently in the list. Now, that T1 comes again, does some compare exchange read between top and old top. And this is implementation defined because old top refers to deallocated memory. So this can do anything, including trap, which is obviously bad. But gets even worse. So let's say we're at this point again. We've deleted node 1. But now we allocate node 3. This reuses the memory of node 1 and successfully added to the list. So now when we do the compare exchange read, this is again implementation defined because all top points to deallocated storage and top points to reuse storage that just happens to reuse the storage we've deallocated. So like bitwise, those two pointers are probably equal. But we've got weird provenance consequences. And like there isn't really any good choices. Like if the comparison returns true because the addresses are the same, node to next pointer will not be updated. It still points to deallocated storage. So we've got the wrong provenance. So as soon as we start iterating over the list, we will have undefined behavior because it points to a deleted object, right? But if it actually returns false because the provenance is different, well, that's not implemented in the hardware because the hardware doesn't know about provenance, right? So this is just a pretty bizarre bug in the C++ standards, right? There's like this code is just broken, and it really shouldn't be broken because all the hardware guys are like, well, obviously this isn't broken. It just does the bitwise thing and it works. But like it's tricky to put that in the abstract machine with the provenance rules. And so there is a new paper. It just was adopted last week in St. Louis at the committee meeting. It makes comparison meaningful. And I won't gonna go into that, but essentially, similar to implicit object creation, we do like implicit provenance updates when doing a reinterpret cast from UN pointer and then back. So when we do this loop with old top, we get like a UN pointer and cast it back. This is not a nowhere because it might implicitly update the provenance to make everything work out. And this is like a bizarre technical detail that you need to be aware of because this is C++. So anyways. Okay. I went over this a bit quick, but you know. Anyways, so let me come to the conclusion and then have some time for questions. So and some actual guidelines. Don't rely on implicit object creation. Right? It's just weird. You start lifetime as or place menu, right? Use place menu to explicitly create a new object. You start lifetime as to implicitly create a new object, right? It just makes the code much nicer to read. You don't have to rely on these redos. You just say, I want to create an entirely new object, or I want to like start the lifetime without touching the values. Whenever possible, use the pointer from placement new and start lifetime as directly, because then you don't have to worry about launder. It will always have the correct provenance. Right? This might not be possible if you're like in some data structure and you don't want to store like 2 pointers. So then you have to use launder, but like whenever possible, do that. And also use a union instead of unsigned char buffers. Union even works in context bar. It's just a much nicer solution. You don't have to deal with any of the weird things. It just makes your life a lot easier. So essentially, like if you're writing code that like sort of relies on some of the stuff I've told you about, you're probably doing something weird. And you have to think about like a different solution. So anyway, that I'm done. I work at Thinksa. We're hiring. I've bought some of our socks, so if you haven't gotten our socks, you can come find me after the talk. We've got the nice L value, R value socks. You will find the slides at that URL. I will also there's an updated errata because the standard keeps changing underneath me while I give this talk. So thank you.